Today, what we are going to discuss and do and observe is the workings of couple of generators and a motor. Okay. Now I'm going to start with the fundamentals. I know you have gone through this either in the class, or if not, you will go through this in the class really fast. But I just want to touch base, make sure we kind of refresh our memory. If not, try to kind of get a feel about this process. Okay. So Michael Faraday, who was a very famous physicist and a scientist, is the first person to understand and study about the interaction between magnetic field and the electricity generator. Okay, this is the foundation of most of the generators we have today. So we have a magnet, a bar magnet, and a loop. So we have a bar magnet, north-south, and a current carrying loop. So in other words, it doesn't have any current right now. This is a continuous conductive loop. It's a piece of wire that is connected to an ammeter. Now what does the ammeter measure? What does the voltmeter measure? Voltage. So what does the ammeter measure? Current. So now this can be used to measure if we have a current in this loop. So now whenever we have, let's say this is our loop. Okay. Now I have drawn it flat. But in reality, I want to envision this like this, because that's the only way I can kind of really see how this is going to move, right? So let's say we have a sitting magnet like this, and I have this loop. Now, of course, I don't have an ammeter attached to this. This is my conductive wire. So the idea is that even if I have my magnet like this, you will still have field lines going through this loop. We have looked at this field lines last time, right? So the field lines are still going through this loop. Now, if you were to look at the ammeter that is attached right here, the current that you will read is going to be 0. Now what he says, what Michael Faraday found is pretty much, if I were to use my magnet and move it across closer to this loop, then I can observe a current. So what is the difference here? So if I keep my magnet right here and keep my loop like this, guess what? The field lines will go and cross the loop, but they will not change. The field line pattern will stay the same. However, if I move it closer or move it away, guess what? The number of field lines that's going to go across this loop will change. And guess what? You will see a current. Okay. So what he says, what is he saying? He's saying that changing the magnetic field will give rise to an electric field, which in other words will establish a current in this loop. Changing magnetic fields, not stationary ones, will give rise to a current in a nearby loop. Okay? So that is established. Now, another thing that I want to say, you may have gone through this, let's refresh. If I have a conductive wire like this, okay? Every conductive wire will have a magnetic field around. Okay? So how do you find the field? If we know the direction of the current, let's say the direction of the current is going up, I take my right hand, put my thumb to the direction of the current, curve my fingers around. Thumb to the direction of the current, curve my fingers around. If I do that, my fingers, the tips of the fingers will give me the direction of the magnetic field around this conductor. So in other words, if I have a conductor like this, with a current going up like this, the magnetic field is going to be like this. tips of my fingers right here will give the direction of the magnetic field. Now remember, we had a direction to the magnetic field last time. When you were drawing magnetic field lines for these magnets, you had a direction, and that is the direction right here. It's not a charge, it's a magnetic field direction. So now, when I draw a single line, is it just a single line? No, it's everywhere. It's up and down. It's like a glove covering this wire. Okay, it's everywhere. Now, twist into this story. We are going to turn this wire and make it a loop. And this is what I have as a loop. Okay, so this is my loop right here. And if I were to have a current going through, my current is given by these shaded arrows. Let me shade them. That's the current. These arrows are magnetic field lines. Remember, like I said, magnetic field lines have direction. Okay? So let's look at this. This is my loop. Now, what I've done is I have taken this and twist it around, made a circle. This is my circle. So this is my ammeter attached to this, and let's say I pass a current. Now of course I don't have a power source attached to this, but let's assume that there is a power source, a battery that passes a current around like this. Shaded arrows give the current. Now if that's the case, when I try to put my thumb to the direction of the current, take my right hand, try to put my thumb to the direction of the current, see what happens. Thumb to the direction of the current. So my fingers will go in this loop, upward. Fingers go upward and in this loop. So I move around and around. I keep my thumb to the direction of the current. My fingers that goes up give me the magnetic field direction and the magnetic field lines. This is why the field lines are coming from the center like this. Okay? Field lines are coming through the center like this. And if you look at the bottom, so you need to make sure that the field lines are continuous. So at the bottom, they come into this loop. On the top, they move away from this loop. Okay? So how do I know this? Put your right hand, thumb to the direction of the current, and then the rest of the fingers you just try to grab the conductive wire. So when I try to grab this, this is the direction I get from my fingers, and that is the direction of the magnetic field. Okay? Now if you look at these two, this field line pattern and the field line pattern because of this magnet, and you should see a comparison. This is north to south, north to south. Field lines are moving away from the top. Field lines are moving away. Field lines are coming and getting together at the bottom. Field lines are coming and getting together at the bottom. Tell me, what would this end looks like if you were to look at it as a magnetic pole? Field lines are moving away. Field lines are moving away. North pole. That's exactly right. This is going to be a north pole. So conversely, what would this looks like? So they come together. They come together. So that is going to be a south. If I have a conductive wire, therefore, if I have a current that flows in the conductive wire in one direction, guess what? You will have a magnetic field line pattern. That field line pattern will decide how the field line is going to emit. Either it's going to come out from the top, or they're going to come together at the bottom. And that will determine whether you will have a north pole at the top or a north pole at the bottom. Okay? So let's say we change the direction of the current. Now my thumb is facing the opposite direction. So not this picture. Now my shaded arrows are moving the opposite direction. So in that case, Guess what? My fingers are now pointing downwards. See? My fingers are now pointing downwards. So that basically means what? It means my field lines are moving down. Now my question is, what would be the pole right here? Field lines are moving and outwards at the bottom. So if I move my thumb to this direction, field lines are moving at the bottom and they are moving away from the bottom. That will be north. That's exactly right. So remember, if I have a current, I will have a magnetic field line pattern. This is true anywhere in the universe. Okay? So now, that is established. Let's move into the real question. That is, what is the direction of the current that gets established whenever you move your magnet? We know that whenever we move the magnet, the field lines are changing inside the loop. We generate a current. Now the question is, what would be the direction of the current in the loop? Now Emil Lenz, a Russian scientist, found that if I were to keep my magnet like this and I were to move my magnet towards the loop, guess what? This loop don't want the magnet to come closer. In other words, this loop will try to push the magnet away. Now if I have a north pole here and the north pole magnet with the north pole is coming towards the loop, how can I push this magnet away? Do I need to have a north pole here or do I need to have a south pole here? Can't hear you. If I want to stop the movement of this magnet, okay, so if I want to stop the movement, I need to push using a magnetic force. That's the only way to push this away. So in order to push this magnet away, I have a north pole here. So the magnet is approaching towards the loop. So do I need to have a north pole here? Because remember, I can create a north. Okay, so what we have is a magnet that's moving towards the loop. So the loop is trying to establish a opposing pole right here to the movement of this magnet. So when it tries to do this, when it tries to establish a north pole to try to repel this magnet, in order to do so, what it needs is a magnetic field with the field lines coming out like this. So that means what? That means I have to establish a current that goes this direction. Because if I put my thumb like this, then the current is pointed with my thumb. So the other fingers give the direction of the magnetic field. Round, all through the loop. So the field lines are coming out like this. Now the field lines, when they come out, they establish a north pole just like this. Of course, correspondingly you would have a south pole just like this. And then of course north and south. Now, in other words, movement of this magnet has established a current that corresponds to the movement of the magnet. Direction of the current corresponds to the movement of the magnet. Let's say for a moment the opposite case. So now you have a north-south magnet, but instead of magnet moving towards the loop, now let's say we are trying to move it away from the loop. Now in that case, again the loop is trying to stop the movement. In other words, it will establish a south pole because this is my north pole. It tries to grab the north pole, attract the north pole, move it back. And in order to do that, it has to make a south pole. And to make a south pole, if we look at the loop, then of course the current has to flow on to the opposite direction where the field lines are moving in. And of course the field lines are moving in, and therefore we have a south pole. And of course opposite direction you will have a north pole because the field lines will emerge on the other side. So now the crux of this story is basically the direction of the motion will determine the established current. In other words, the direction of the established current. That is very important. In a proper, dynamo, or in other words, a generator, you have many loops like this, not just a single loop, many loops like this, helping to generate the current in the generator. Now, every time you have a loop like this, what you establish is what we call an electromotive force that gives rise to the flow of current. So, it's an induced current. This motion of the magnet, or in other words, change in magnetic field, induces a current who generates an electromotive force of the loop. Now, for today's lab, you're going to see DC currents and AC currents. We have three types of generators. We have a generator that we will use to generate a DC current, and we will have a generator that will generate AC current. And then we will have a generator that generates both DC and AC. Now, if you have an ideal case, your DC current would look like a flat line like this. Ideal case, if you have a most probably if you have a dry cell like a battery, like a small AAA or AA battery, you will get a flat voltage that does not change the polarity unless you flip the battery. But what you will see today, because of the generator, DC generator, it's going to have fluctuations like this. That is because it's not a smooth generator. And also another thing is that when you rotate the generator in the opposite direction, you will see that this pattern will flip the sides. That will be another indication this is a DC generator. Now, for the AC, you will have a nice sinusoidal curve if it's an ideal scenario. But in our case, we will have a jagged, kind of rough waveform. This is what you're going to observe. Okay? So, I did this part as an added part to the first because, unfortunately, the first part of this got cut off. Okay, so today you will have a motor for the laboratory part. You will have a generator, 3 generators, 1 motor. So what you will have is a power supply that will establish a current that passes through. You can record the current using the ammeter, and you have a voltmeter. This is your motor. We will measure the current and the voltage, and then we will write it without the loop. In other words, we will not apply a load onto this motor, and we will record the voltage and the current, and of course we will record the power. And then we will apply a force. We will try to hold the motor down. So in other words, we will have a load on the motor, and then again you will record the voltage, the current, and then P times power is equal to V times I. Now remember to convert the current into amperes, because what you will need is milliamperes. Okay? So let me start one of the tables, and then we will start together afterwards. Okay?